Bismillahirrahmanirrahim. Uh, Today, I was thinking to start talking about X-ray diffraction, right? But when I looked into that, it needed a little bit of my study as well. That is why I postponed it to the next lecture. And I'm still keeping the same track that how you engineer materials. The main thing is I need you to have a hands-on experience. Pick up things. What is engineering material? I have given this example several times that making tea, I am not making things difficult. I am making things easier. When you make tea, you need that caffeine for your body. But when you boil caffeine, the tea leaves in water, its taste is not good. It doesn't feel good. For that purpose, you put a little bit sugar, right? To change the taste. Then again, it is very harsh on your throat and maybe acidic a little bit. So you put alkaline material milk upon it, right? So you engineer your cup of tea to become drinkable. The same thing is in the engineering of material, that you collect a few properties together, that I need something. For example, you are making car. You are not making car with engineering materials. Know this, because people will ask you. You are not making cars with engineering of material. You are making or engineering the material for specific application. The material for specific application. So how would you like to have a car? It's, for example, external body. Heat is not transferred easily, so a little bit heat resistant. Mechanically, it is sound, so that in case something unusual happens, it protects your body. Thirdly, its weight is not that much that when you consume petrol or diesel or whatever, it is not totally consumed to carry the weight of the car. So this means you need lightweight, excellent mechanical properties, and heat resistant material. You got these three, the set of properties. This is a set of three properties for body material. Now you engineer material for it. Can you choose glass? The answer is no. It is not mechanically sound. Can you use something which is, say, rubber material or like that? No. It's fixing, shaping, shapeability. These things are compromising. So you ultimately decide to go to metal. Then in the metal, you take a basic metal and measure its properties. Then how much is its mechanical strength? How much is its density? And thirdly, how much is its mechanical strength, density, and shapeability, right? It withstand the shape or not. When you decide that, then you substitute thing. For example, the car material should not rust. This means it is better to use aluminum or steel, stainless steel for that body. So in this way, you modify the material and you come out with a new material which has all these properties. For your kind information, around the world, I published it in a book as well. Two things. A very high strength material by MIT had been introduced a few years back, which is called frozen smoke. Frozen smoke means it is almost weightless, but its strength, toughness is 10,000 times more than the toughest known material on earth. So when the weight is so much ups, almost negligible, and the strength is so much high, how big a revolution it can bring in the aeronautical industry. Where weight is the problem, where strength is the problem, right? So you are, for example, if you are using rocket nose, the rocket nose is not only should be mechanically stable when it is fitted into the front of the rocket, but it is mechanically stable when the rocket flies or moves in a temperature of minus 60 degree with that much resistance of the air. So for that people use a modified form of lithium disilicate, spodumene type material, which is a modified form of lithium disilicate. So engineering is that. Now I gave you first the example of the simplest clay-made bodies, which the Chinese made, and they ruled over that for many years. Now coming towards a little bit technicality. Here I am making a material for cell phone application, for wireless microwave communication systems, right? For that, I don't have the ready-made material from nature. If I mine it, I frame it, shape it, and use it. No, there is no such material which has all the properties all together in one material. Then I look, as I told you, to the setup properties and look into various materials and literature, and they say that strontium niobate is ferroelectric below 16-15 degree Kelvin, right? Okay, it's a good material. Titanium has excellent dielectric constant. Always there is a specific range for the properties to be applied. If the signal, notice it carefully, if the signal travels more distance within the device, when the signal has to travel more distance within the device, then the device permeability counts more. The device permeability and loss counts more. But if the signal is traveling for 1,000 miles in free space and the device is here and here, that traveling distance in the device is too small, then people don't depend too much on the device dielectric constant. So if you make a material which has excellent TIF and QF, if they have excellent TIF and QF, but the dielectric constant is poor, it is not suitable for the your cell phone application, say. It may be excellent for radar application. It can be excellent for antennas to be used in antennae, right? So sometimes you engineer materials for your required specification. Sometimes you engineer materials according to your requirement. Sometimes you get excellent properties from the material and you look applications for those. So both the ways you are supporting the humanity and industry, right? Either you design equipment for specific application, or sometimes you find excellent properties and you look application for that which bring comforts to human life and which are affordable. Then, so you found that these three things three initial ingredients are known in literature that they have these properties. Then you combine them. How much sweetness you want, how much you like the tea to be sweet. If the IO2 is sweet, then add it more. If you don't like too much sweet, then a little bit less and the other more. Right? Secondly, caffeine. Do you want more caffeine or less caffeine? Then change the tea leaves concentration within. But not like that it is a shopkeeper balance and you have a teaspoon in your hand and you are decreasing and increasing. No, scientifically. And what scientifically? Is the coming material which you are planning to make single phase or not? This is the first thing. If you are interested in minimum loss and uniformity of property, uniformity is must, because a slight variation in communication can crash aeroplanes in the sky. So the science is not a rough, tough job. It is very precise. A small instrument in the passenger aircraft is hit by a bird, and many people died in several crashes because of that. Because that device is working as a sensor, and when sensor is not there or it's malfunctioning, then you are killing people. So the scientist must be very precise, and that is why people again and again emphasize upon repeatability, that you standardize, optimize the properties. So when you select these, then which phases are possible? And you again go to the tertiary phase diagram. Now, if I keep the amount limited to here, right? If I keep the amount of this ingredient to here, I will get this, this, and this. So the ratio will be in this triangle, and I will get that place. And this is the tie line. From one line to the other, this phase will form. Now, the chemical composition calculation shows you that this phase will form. Is it really forming or not? Is it really totally crystallizing into the same material or not? For that, you take that composition here. If you are going into from this, they are equal. But if you are taking here or here, then you are making different triangles, because it will be described by the tertiary phase diagram. Up to now, we are talking of binary phase diagrams, right? And quaternary and tertiary phase diagrams can also be introduced. And you check that which phase can form. And again, you are, for example, putting SR6, TI2, NB4, and 420. Look at it. Calculate it. SR4, SR6, it is plus 2, right? So it is plus 12. TI2, plus 8, 20, NB4. NB so NB2 05 05 10, so it's plus 5. Is the equation balanced or not? You will have to check it. If the equation is not balanced, then whatever you are making will not be a stable phase. There will be deficiency in it, deficiency of oxygen. Deficiency of oxygen in a material structure means that you will have gaps. unfilled cation anion sites inside the crystal structure, and that unfilled sites will again confer either good or bad properties depending upon the application of the material. Then, if you follow this line, then there are some compositions here which meet the stoichiometry. The standard stoichiometry is met, but is it energy-wise possible to make that particular phase or not? It comes from the experiment and from the detailed theory. So you look into these things. Now, when you look into these things and you do XRD of these, start from here. This peak is common, this peak is common, these peaks are common. So the material is almost single phase, and I have changed here the Y. The formula is there. 1 minus Y SR4 NB4O14 Y SRTiO3. So it contains all the three contents: strontium titanate, titanium, and strontium niobate. There are numerous ways of how to add things. Are you substituting the cations? Because you are putting many different things together, but the unit cell is the same. The unit cell is the same. It is the unit cell like this, and you are changing this. That if you have 100 unit cells and in 50 you are changing the B side cation. There are 12 million unit cell and you are completely changing the B cation. So when you change the B cation, the volume of the cell will change. When the volume changes, the symmetry changes sometimes, if it is too much change. Then you put the condition that if I am changing this, if I am changing this specific cation, and they are affecting A, B, and C, will they equally change? Will they equally change to keep the structure the same, or will they change differently to change cubic into tetragonal, to change cubic into monoclinic or orthorhombic? So we are looking for something, because the properties are not given by the chemistry alone. The properties are given by the crystal symmetry as well. So I am interested in both the chemistry as well as the crystal geometry, the crystal symmetry, chemistry as well as symmetry, because symmetry goes the electronic and electrical properties, and the chemistry goes the intrinsic property of the relevant material. Now, if I substitute here a cation which is more than 15% larger than the host cation, it will not form that phase. And that 15% comes from the tolerance factors and those. So when you calculate that this specific structure will form or not, so conditions increased. The material scientist conditions increased. Chemistry, stoichiometry, chemistry, stoichiometry, crystal symmetry, and then that structure. Are we taking the fundamental structure, or we want to distort it to the new structure? So small variation will bring about distortion, but it will not affect the original symmetry of the crystal. Right? Small variations will change will bring about the distortion inside the crystal, and this distortion leads to the electrical properties within the material. So you are free in the world. As many cations you want to add or remove, you can do it, but all under specific scientific rules, so that instead of benefit, you don't damage the system. If you change this one cation, if its size increases, it creates tension inside the unit cell, and that tense situation restricts the movement of ion. If you put smaller cation there, what will happen? The cation will find more room to oscillate or respond to the electric or magnetic field. It will have more room to respond to the applied electric or magnetic field. More response means more polarization. More polarization means more work, more ferroelectricity. Right? So the size, the chemistry and the geometry all are together gone, and it is like a benchmark that you are looking for single phase. So I change the value of Y because I am introducing titanium. Strontium is already there, but I can't add titanium blindly. I am making a solid solution, and I have explained the solid solution that it is not something as you say mixture. I had explained what is mixture, what is solid solution, right? And the two ways people add things: additives. When you add something, listen this carefully. Additives are adding some material, some compound in such a way that its amount is too little. Its amount is too little to change the crystal structure or property. Additive whose amount is too little to change the crystal structure or properties, but just enough to change the processing temperature. For example, you are interested in decreasing the temperature, and you add, as we did in the case of the vitreous ceramics, that you add something, some low melting phase, to make the ion and the cations move to reorient themselves, to reconnect themselves and form new phases. So the additive and substitution are completely different things. Substitution means you are substituting or putting or replacing a host ion with a foreign ion. And additive is something blindly thrown into the material. Right? For example, you put kerosene oil on wood to accelerate fire. So that at the end, that kerosene oil is not there. It just helps you. You put binder in a material. So the same thing is there, that you are not interested in titanium dioxide, for example, but titanium dioxide accelerates the chemical reaction inside there. It helps in densification of the material, and the compromise because of this unwanted ingredient on properties is not that much. Is it possible that you put chili in something and they will not be hot? When you put chili in something, it must be hard. So this newer means that titanium dioxide or whatever additive you put there, it will not change the system. It will change the system, but you are keeping it to such a low level that that much change can be acceptable, right? That change will be compromisable. So never think as a scientist that you put something new and it will not bring any change. It will bring change, but that change be within the acceptable limits. For example, the material had a dielectric constant 50, and because of that addition it became 45, but 45 is still not bad. Then in that case you decrease the financial costs of processing material and little bit compromise on the property which is acceptable within that limit. So if I do a study of these material and they are all giving me a single phase, obviously slight variations will be there. A peak will shift when I replace niobium with titanium. The ionic radius of niobium and titanium are almost matching. They are about 68 or like that, as I remember, but you can check it. For ionic radii list, the ionic radii are different in different situations. If a cation is in 8 coordination, it is enclosed or connected with 8 nearest neighbor, its ionic radius will be different. But if it is in 12 coordination, the nearest neighbors are 12, then its ionic radius will be different, completely different, right? Not small difference. So because it is an electromagnetic system, and when you change the number and quantity of charges around, obviously the ionic behavior will change, and that is why 8 coordination and 12 coordination ionic radii are different. And Shannon SH ANNON 1992 and 1976. These are 2 papers. When we were student and we used to read, maybe nowadays people have found some more, but this is the ionic radii data for 8 and 12 coordination of elements. Shannon is the author, and when you give Shannon 1976 or 92, I don't exactly remember the 91, it is 90 or 92, but the 76 I am sure about that. So people take the ionic radii data from there. So when you are replacing or substituting a cation here, you must have the idea of ionic radii and its impact. But if the ionic radii is matching, the host ion and the subsequent ionic radii are matching, then why I am replacing it? Right? Because the polarizability is different. When the polarizability is different, the more polarizable a cation is, the more ferroelectric the material will be. So it enhances the property by replacing that particular cation. If the phase is single phase, then I am happy with it and I will go ahead. If still the theoretical properties are not coming from the material, the phase has been formed, it's exactly the same what I wanted, it is a single phase, the latest parameters are consistent, everything is consistent, but my properties are not that what I was expecting from 100 grams of sugar. The tea doesn't reflect 100 grams of sugar. This means there is something else in it, and that something else, at first glance, the material scientist should come towards the density. That am I wearing the optimally dense material properties, or I am wearing air property as well. If there are voids and gaps and pores, say, in a material, then how much porosity is there. If there is 5% porosity or less, it is acceptable to some extent. Try your best to go to the optimum level, right? But up to 5% is acceptable in the telecommunication device applications. But if it is beyond 5, more than 5, then your properties are not the optimum properties. It increases the losses because your material is giving you the property, not the free space there. So it will increase the losses of the signal. Secondly, it will compromise the other properties. The material dielectric constant is, for example, 5,000, 10,000, and the dielectric constant of free space is 1, then it will be in that ratio there. And people can calculate it, that how much dense the material is and how much value for the property I am accepting. So when the single phase is formed and it is not giving the property, your next thing is then microstructure. Look into the microstructure of the material, that the phase I want it formed, but the property is not there. Then let us check the density. The density, from where does the density come? From the microstructural arrangement of these grains, right? These are the properties. I looked into for that material which was single phase, right? I looked for that material, and this is the temperature and that is the dielectric constant. Now I smoothed the dielectric constant for example, some of the excellent materials, say barium manganese, is like this. But here I got the dielectric constant like this. What does this mean? This means that the dielectric constant is stable at all the possible operational temperatures, starting from the room temperature up to 70 degrees. It is smooth. So it is an excellent property and shows the stability of the dielectric constant with temperature. And here, where there is 0, it was like this. Now, is it all? Because there is also a big word below 20 and above 70. There is a big word below 20 and below 70. It was that thing, it went like this, and it suddenly came like this. It came down. So just a couple of degrees after that, it peaks out. And maybe the material is excellent above that. What does this mean? This means you must quote a reference. If you are studying it from 20 degrees or 25 degrees, I have done it from 25 degrees, up to 70 degrees, why are you not going beyond and above? There must be literature proof that yes, that Mr. That have done it, and it is that property. It is not beyond that, right? Because if you start measuring the dielectric constant of a single material and start from minus 273 and going up to 10,000 degrees, do you need it? You never apply a material at 10,000 or 2,000 degrees centigrade. Also, there may many changes may occur, but after some time the material will melt and you will be sitting near the experiment to find your sample, and tomorrow you will blame people that somebody has stolen my sample and it has been burned. I have seen many people. moving angry around their furnaces that last night I put this sample and maybe that person has taken it. And I asked them at which temperature you were heating it. And when they said, I told them just go to the phase diagrams and check the melting point of that material, or there may be some materials undergoing sublimation or different things at different temperature. So there must be a logic always. Whatever you do, there must be a logic. But if you present your thesis to me and you show me these plots, then my first question will be, what happened at 80 degree? What happened at 90 degree? What happened at 150 degree? What was the situation at 500 degree? And you will tell me that I checked this literature, and according to them, no change is occurring beyond there. Then your thesis and statement, if you look into the start, how you say it and why you say it, these two questions must be answered. On the basis of what did you say this? Does the machine measures dielectric constant? The answer is straightforward, no. The machine is not measuring dielectric constant. The machine is measuring the capacitance of the sample. And the capacitance is converted into the dielectric constant. So you must know the background of your experiment, the logic of your experiment, and the systematic approach towards your experiment. Then you will be able to move forward.